thank you all for standing by, and welcome to the second webinar of our spring series entitled Climate Change Impacts on Great Lakes Water Levels. These monthly webinars are an initiative of the Ohio State University Climate Change Outreach Team, a multi-departmental effort within the university led by OSU Extension, Ohio Sea Grant, Bird Polar Research Center, and 6 other OSU departments to help localize the climate change issue for Ohioans and Great Lakes residents. I am Jill Gentis-Banicki from Ohio Sea Grant and Stone Laboratory, and joining me today is Dr. Drew Grunewald from NOAA's Great Lakes Environmental Research Laboratory, or GLERL, in Ann Arbor, Michigan. Dr. Grunewald is a hydrologist at NOAA GLERL, where he conducts research on watershed hydrology and water quality, focusing on measuring the uncertainty in environmental processes and using this data in models to help inform water management decisions. Prior to joining NOAA, he worked as a scientist within the U.S. EPA and also as a professionally licensed engineer in the environmental consulting industry. We're delighted to have Dr. Grunewald here today to discuss how a changing climate could affect our water levels in the Great Lakes. But before we do that, a few logistical issues as we get started. During our presentation, all participants will be in a listen-only mode. Afterwards, around 12:45, we will conduct a question and answer session. If you would like to ask a question during the presentation, please feel free to use the chat feature located on the right-hand side of your screen, and I'll collect and pose the questions out to Dr. Grunewald at the end of his presentation. Because there will be data sets that you may want to see full screen for detail, feel free to view full screen during his presentation by going to the bottom left-hand corner of your screen and click on the full screen icon. It's the third icon from the left. You'll still have the option to ask questions via the chat by clicking onto the conversation bubble in the lower right-hand corner of your screen. And please do ask those questions. We have more than 200 participants on this webinar, a great diverse group representing governmental agencies, academia, and nonprofit groups from the Great Lakes and around the country. Please keep the questions coming throughout the presentation, and we should have a great Q&A session. As a reminder, this webinar is being recorded and will be posted onto our website for later viewing. Also, we will post a webinar survey in our chat feature toward the end of the hour. Please take a few minutes after the webinar to fill out that survey. It will help us continue to bring you better webinars. So without any further delay, I'd like to introduce Dr. Drew Grunewald from NOAA's Great Lakes Environmental Research Laboratory, who will present climate change impacts on Great Lakes water levels. Dr. Grunewald?
Thanks, Jill.
All right, I am going to give you the ball.
Okay. I just switched over to my slides, and they should be up there now. Okay, Jill, thanks. Jill, are my slides up now?
Your slides are. You look great.
Okay. Thank you, everyone. Thank you, Jill, and thank you, everyone, for taking the time to call in. Again, my name is Drew Grunewald. I work here in NOAA's Great Lakes Environmental Research Laboratory here in Ann Arbor, Michigan. I'm going to start off today by providing a little bit of an introduction to this research and highlighting some of the reasons why I think the research that we're doing on climate change and water levels in the Great Lakes is so significant. And then I want to dive into a look at some of the data we've been collecting, not just water level observations, but also data we've been collecting on various aspects of the meteorological and climate system as well. And then I want to take a look at how we develop and use different models that represent and interrelate those variables to the best extent possible. And then finally, we'll take a look at how we propagate different regional climate scenarios through a process called downscaling into those models to get an idea of what we might expect for water levels in the future. So to begin, those of us who live, work, and play here in the Great Lakes recognize that it's an invaluable freshwater resource. It serves as a source of recreation and tourism. It has unprecedented natural beauty, and it also serves as a home to on the order of 30 million people, many of whom live right along the coasts of the lakes themselves. The image that I'm showing you here includes an outline of the Great Lakes watershed, which is this thin line you see here, and then each one of the individual little yellow dots you see represents around 2,500 people. What this image underscores is the fact that many people live in these cities that are nestled right along the lakes themselves, and that changes in the water levels can have a profound impact on human and environmental health. The Great Lakes also support a large commerce industry. There's a lot of information on this screen, but there are three sort of key features that I want to highlight for you, one of which is the fact that each of the circles you see on this page represents the magnitude of shipping in that particular port. For example, if you look at this circle here, the magnitude of that circle, or the diameter of that circle, represents the relative magnitude of shipping that was done in that port, which is Duluth, and this is back in 1990. Even though this picture was generated a while ago, the general trends here and the take-home messages are the same. The second take-home message from this particular slide are these purple arrows that you see in between each of the Great Lakes. These represent the magnitude and direction of the shipping within the Great Lakes. And then the third and final take-home message regards this profile image you see up in the upper right-hand corner, where we're looking at the flow of water essentially from Lake Superior and Lake Michigan, essentially downhill through Lake Huron, Lake Erie, and then down into Lake Ontario. What this profile underscores with reference to shipping is the fact that while the Great Lakes are relatively deep, the internet-connecting channels and canals are relatively shallow, and changes in water levels can have a profound impact on that industry. Now, all of this is sort of put in the lens of some of the recent water level declines we've been experiencing over the past 10 to 15 years, particularly those we've observed on the Lake Michigan, Huron, and Lake Erie system. And there have been a variety of reports that have sort of captured these observations, one of which was presented by our colleague here at GLERL, Craig Stowe, in a cover article in Environmental Science and Technology recently. One of the potential impacts of these water level declines, as an example, again, is the impact on the shipping industry. If we look here at an aerial photo of a vessel approaching one of the locks on the St. Lawrence River, this picture sort of underscores the fact that these canals and these locks are narrow and also very shallow. And as water levels drop, it forces ships to carry less payload, and it also forces perhaps an increased rate of dredging in order to lower the bottom of these canals in order to support the industry, both of which have, of course, significant cost implications. There are a broad range of other effects as well of lower water levels, not just transportation, but also tourism and recreation, impacts on the fisheries industry, which Stu Ludson in the last webinar in this series did a great job of summarizing, all the way down to impacts on human and environmental health. So the take-home message of this particular slide is the fact that for any given water level, on this particular slide we're looking at low water levels, there are an associated range of potential impacts. What we're trying to do here at GLERL in our climate and hydrological modeling programs is try to get an understanding of how different future climate change scenarios might impact water levels, and then work with managers and other folks in the Great Lakes to get an understanding of how the range of anticipated water levels could lead to a range of potential impacts, and how different risk-based management decisions can take that variability into account. Now, one of the things we try to do here at NOAA, and in particular here at GLERL, is of course provide research that helps protect human and environmental health and commerce and the economy in the Great Lakes, but we also like our research to have as broad an impact as possible, perhaps even on a national or multinational, even a worldwide scale. In order to do that, we need to put some of the problems we're facing into an appropriate context. And I want to continue with the example of some of the data from the shipping industry here. What we're looking at here is a table that's going to rank the ports of the United States in terms of total cargo volume. And if we start off with this list, the first on the list is the Port of South Louisiana, which in 2009 handled about 213 million tons of cargo. And if we continue on down this list through the top 10, what we see here is that the ports of the Great Lakes don't fall on this list. In fact, one of the inland ports in the United States does fall on this list, the Huntington Tri-State Port, which is 8th in the United States in terms of total cargo volume. To get to the Great Lakes, we have to go all the way down to the 25th highest ranking port in terms of total cargo volume. And then the next highest port in the Great Lakes is 36 overall in the entire country. So what's my point of showing this slide? Well, we could generate a slide like this for other sectors of the economy and other impacts on human and environmental health here within the Great Lakes, and I think we might find a similar story. So the point is that while these impacts are certainly significant within the Great Lakes, and they're significant on a national scale, they alone are not going to capture the kind of attention that we're looking for in terms of funding, in terms of resources, in terms of publicity that we're going to need to help solve these problems. Now, I may be a little bit biased in this perspective, but I believe that these data, coupled with the fact that we live in such a fascinating hydrological and water resource system, is what really drives home the major selling points of the problems we're facing. One image that helps underscore that fact is this one here, generated here at NOAA, which puts into perspective the extent of the coastlines that we manage here in the Great Lakes. So what this image is showing, along the right-hand side of the screen here, are each of the major Great Lakes flipped, rotated, and in some cases, even with these two, this is Lake Michigan, split in half, to show the extent of the United States borders of the Great Lakes relative to the entire eastern coast of the United States. And what you see here, of course, is that the two are of equal magnitude. This is important because when we look at a lot of the ongoing discussions right now about climate impacts of coastal regions of the planet and even the United States, the coastlines of the Great Lakes are not always included in that discussion. Yet I believe that the management strategies and the adaptation measures we're taking and the impacts of climate change on water levels that we're experiencing here in the Great Lakes are on the same order of magnitude as those on major coastlines and could serve as an important precedent for future management and future research. When we look at this picture on a worldwide scale in terms of freshwater resources, and we take a look at what I'm going to refer to as continental water bodies on the entire planet, and we rank the top 12 of those, here's what we see. Now, we could debate whether or not the Caspian Sea is a lake or a sea, but it is technically classified as a continental water body. Now, when I highlight the water bodies on this table that are within the Great Lakes, we see an interesting picture emerge here. For example, if we remove the Caspian Sea from this list, for example, and we add up the Great Lakes in terms of total collective surface area within the Great Lakes freshwater resource system, nothing else on the planet comes even close in terms of total freshwater resources that are available. When we look at the Great Lakes on a volumetric basis, we see that the Great Lakes as a system fall in the same order of magnitude of the top 3 freshwater resource systems on the planet, along with Lake Baikal and Lake Tanganyika. So what does this represent? Well, what it indicates is that the Great Lakes are a fascinating and vast hydrologic and freshwater resource. That fact, coupled with the fact that they support such a large population and serve as such a large source of commerce, shipping, industry, and tourism, makes them certainly worthy of a lot of research and a lot of publicity. So what are some take-home messages from the introductory part of my talk here? The Great Lakes are certainly one of the, if not the largest freshwater resource system on the planet. They support a significant population on the order of 30 million people or so, and they support several sectors of the economy. And they're collectively managed by 2 nations. The United States and Canada work quite well together to manage this rather complicated resource. And all of this points to the fact that the Great Lakes really could serve as a wonderful benchmark for both adaptive management and also for hydroclimate research. All right, next let's dive into a look at some of the observations we've made here in the Great Lakes over the past 100 to 140 years with regards to water levels and also with regards to climatological variables. Now, before I take a look at any data, I want to give you an idea where some of this data comes from. What we're looking at here is one of NOAA's water level gauging stations. This one happens to be in Mackinac City. And what we see here is a small little housing unit with some meteorological data collection equipment. Within this housing unit, there is a small sump down in the bottom, and within that sump, water from the Great Lakes, or from this particular lake, can flow freely in and out. And there are sensors in the bottom of that sump, pressure sensors that can help record water level information. Now, these gauges are located all throughout the Great Lakes, and there are many sources of short and long-term variability in these measurements that make it somewhat interesting and challenging to combine the information across the entire Great Lakes to get an idea of what's happening over time. One of those sources of uncertainty and variability is related to the idea of isostatic rebound. And what that is the idea that the surface of the Earth in the Great Lakes region in particular is changing in response to the relief in pressure from the glaciers that have retreated since the last ice age. So what are we looking at here? Well, in this picture, what I'm doing right now with my highlighter is I'm tracing the outline of the Great Lakes really quickly so you can see that's where they are. And then these black dots along the shores of the Great Lakes here are where the United States and Canada maintain their water level gauging stations. Now, take a look again at these contour lines that I'm highlighting. I'm highlighting right now a zero contour line. What the zero and the other numbers that you see here indicate is the change in the surface elevation of the Earth, or the relative change, in terms of centimeters per century. Now, that may not sound like a lot, but if you look, for example, along the northern shore of Lake Superior here and the northern shore of Georgian Bay, we're experiencing a rate of change at the surface of the Earth at a rate of anywhere between 30 and 50 centimeters per 100 years. And what that implies is that perhaps over the course of somebody's lifetime, the surface of the Earth there might have risen on the order to a foot or a foot and a half. Now, that may not sound like a lot, but there are some pretty significant implications for that, one of which is that a lot of the infrastructure up there was put in place 50 to 100 years ago. And also, given the way that the bottom of the lakes changes in terms of slope, a foot to a foot and a half of water level change, in this case a water level drop, can have a significant impact on the perceived shoreline there. So again, this is just one of many sources of uncertainty and variability in water level measurements that might not be readily apparent when we look at a lot of the data. Okay, so what I have here is an empty plot on which I'm going to show you water level data for the major Great Lakes. On the left-hand axis over here, I have a range of numbers that represent water levels in meters. And I have a unit of measurement here called IGLD 85. What that refers to is the International Great Lakes Datum from 1985. In order to establish a common reference point, we utilize a 0 point or a reference datum point, which is this IGLD point, and that is updated every 30 years or so. The first one was established in 1955, it was updated again in 1985, and it'll be updated again in 2015. That benchmark serves as a reference point against which both the United States and Canada can compare the measurements at their water level gauging stations. So on the x-axis here, I have time ranging from 1860 all the way out to 2100, and then on the right axis here, I have the exact same water levels, but just simply converted over into feet. So let's take a look here at Lake Superior. What I've shown on the screen is the annual average water levels on Lake Superior from 1860 until present, and I can put a red horizontal line on there that represents the long-term average over that time period. I can repeat the same procedure for the data for the other Great Lakes, and we see some interesting patterns emerge here. One of which is that there seems to be much less natural variability on Lake Superior relative to Lake Michigan, Huron, and Lake Erie, and also relative to Lake Ontario. Of course, Lake Superior and Lake Ontario are both currently regulated. The regulation on Lake Superior began around 1920 or so, but we don't really see a dramatic response to that regulation activity. On Lake Ontario, regulations began on the water levels right around this time period, and perhaps we do see a dampening in annual water level fluctuations during that time period. A few other points to underscore on this slide are that Lake Michigan, Huron, and Lake Erie seem to respond in a similar way in terms of changes in water levels over time. In particular, we see that there has been a significant drop that we recently experienced in the past 10, 15 years. And while that drop was not entirely unprecedented, for example, we've seen similar rates of drop in the past, what is somewhat unique about this last drop is that it has not been followed by a rebound to the same rate that we've seen in the past. And one of the research questions we're asking here is, what caused this significant drop, and do we expect some type of rebound, or have we entered an entirely new hydrologic regime? Now, I can put on top of this, what we're looking at here are annual averages. There is certainly variability at different temporal scales as well. For example, I can put on top of this monthly average water levels, which is what these light blue dots here are here on Lake Superior, and I can repeat that for the other lakes as well. And what we see here is not only the fact that there is certainly variability on a monthly scale above and beyond the annual scale, but there appears to be significant additional variability as we move down through the lakes particularly when we look at the monthly variability on Lake Ontario? Well, there are a lot of explanations and potential reasons for this, but one of the more dominant ones is the fact that water is flowing through the Great Lakes towards Lake Ontario and is essentially accumulating. So what we're doing here is we're effectively tipping a large diameter bucket into a relatively narrow diameter cylinder, and the response in the surface elevation of that cylinder is going to be more dramatic as it is in Lake Ontario, which, if you recall from the table I showed earlier, Lake Ontario has the smallest surface area of any of the Great Lakes. Now, I want to be consistent with my message of putting a lot of this, the lake level responses to climate change in a national perspective. What we're looking at here is an image from NOAA's Climate Services webpage, which I'll put up at the end of my talk, but it's at www.climate.gov. This is a very valuable tool that's on that webpage called the Global Climate Dashboard. And I want to draw your attention to the fourth panel down here, which shows sea level rise over the past 100 years or so. And when you take a closer look at this portal on the Climate Services webpage, you get directed to a water level gauge in New York City that indicates the same trend we see here of a continuous rise in water levels. I thought it might be helpful to put that water level rise that we're experiencing on the eastern coast of the United States into some perspective. So let's take a look here again at the historical water level data here on the Great Lakes. Now, right around here, I'm going to put in the monthly average water levels from this gauging station in New York City. The water surface elevation there, of course, is closer to 0 than it is to 180 or so, but the extent of the y-axis I'll be using is the same. So here we go. I've just put on there the monthly average water levels from this water level gauge at a location called the Battery, which is at the southern end of Manhattan Island. And so what you see here are some interesting features, one of which, of course, is that it does indeed appear that the sea level on the eastern coast of the United States, represented by this particular gauge, is rising. But the order of magnitude of the rate of change and the rate at which it is rising doesn't even come close to the rate of change of water levels that we've been experiencing over long-term time periods here in the Great Lakes. And certainly there's an awful lot that can be learned about how the Great Lakes have adapted to those changes that can probably be transferred to the east and west coast of the United States and other coastal areas as well. But another take-home message from this image that you're looking at right now is that the Great Lakes have one of the, if not the longest periods of record of climate and hydrology information on the planet. And that alone can also help serve as a valuable source of information and research for other areas to learn from. Okay, now there are other sources of variability as well. I've shown annual and monthly variability in water levels. There's variability on weekly, daily, and hourly scales as well. This image shows how we might have variability in water levels due simply to changes in local weather patterns. What this schematic indicates is how a dominant wind pattern passing across the lakes might cause water levels on the downwind side of the lake to rise, but on the upwind side to actually drop. And this phenomenon has been observed on the lakes in the past. One of the classic images expressing this phenomenon is this image that is taken from a storm in early November 1955. And what we're seeing here is this solid line represents water surface elevation at a gauge in Buffalo, and the dashed line is a gauge in Toledo. And what we see here is that this storm caused a rise in the gauge at Buffalo of roughly 8 feet or so. At the same time, there was a drop on the western edge of Lake Erie at Toledo of about 5 feet or so. That's in response to what we call the storm surge. And then what's interesting is that after that storm subsides, Lake Erie essentially sloshes back and forth through a phenomenon we call the sesh, where the water levels rise and fall in this periodic manner. Again, this is an indication of some of the type of short-term variability that we might experience on the Great Lakes. And when we talk about changes and impacts in water levels on the Great Lakes, we really need to consider all these different scales in concert when we look at how they might impact human, environmental health, and the economy. Okay. Now, one of the questions we're looking at here is, well, what is impacting the Great Lakes water levels? Certainly, one of the major factors here is the major components of the hydrologic cycle. Let's take a look at the hydrologic cycle of the Great Lakes to get an understanding of what's at play. And this image here obviously contains a lot of information. It's taken from US EPA's website. What I want to focus your attention on here is the middle, which represents the major elements of the hydrologic cycle. So we have this cloud up here, but we have these 5 arrows here, which are representing 5 major components of the hydrologic cycle in the Great Lakes. This arrow on the far left here represents evaporation from the lake surface. The next arrow over represents evaporation from the ground surface. And then this next arrow represents transpiration by plants. Moving over, we have precipitation on the ground surface, which eventually works its way into the lakes either through groundwater or tributary flow or even direct runoff. And then finally on the far right, we have precipitation on the lakes themselves. Now the width of these arrows represents the relative magnitude of each one of these sources or components of the hydrologic cycle. A fascinating feature of the Great Lakes watershed is that over-lake evaporation and over-lake precipitation represent 2 major components of the hydrologic cycle. That is somewhat unique when you look at most hydrological modeling studies and rainfall runoff modeling studies. What is even more interesting is that when we look at that even closer, is it's very difficult to measure over-lake evaporation and over-lake precipitation. Yet these are sort of the 2 major pieces of information that we need in order to make accurate water level forecasts. Now, when we develop models of the hydrologic cycle here in the Great Lakes, we tend to lump these major components into 3 categories, and those are represented by the 3 arrows that I'm circling here on the western edge of Lake Superior. These 3 areas, what they represent, the green arrow represents runoff, in this particular case, into Lake Superior. The orange arrow represents over-lake precipitation, and the red arrow represents over-lake evaporation. Again, the width of those arrows represents the relative magnitude of those 3 sources of the hydrologic cycle. If we look through the entire picture here, we see some other significant features. These purple arrows represent the magnitude of flow of water as it goes through the Great Lakes system. And finally, I also want to highlight some of the diversions of water into and out of the Great Lakes watershed. In the northwest corner here, we see the Agoki and the Long Lake diversion that each contribute some water into the Great Lakes watershed through Lake Superior. And then, of course, we have the Chicago diversion down here out of Lake Michigan that draws water out of Lake Michigan. And finally, we also have the Welland Canal, which runs somewhat adjacent to the Niagara River between Lake Erie and Lake Ontario. Now, there have been a lot of studies that have documented the impacts of these diversions on the Great Lakes. Some studies suggest, for example, that the Chicago diversion lowers Lake Michigan on the order of a few inches. But there are also some studies that suggest that the overall effect of water levels of the diversions sort of balances each other out. Nonetheless, the point is there are a lot of factors here that are interplaying at various spatial and temporal scales that we're going to try to keep track of in our models. Let's take a look at how these variables have been changing over time, perhaps in response to, as a part of the overall climate change regime. So let's take a look first at precipitation. I'm showing here again an empty plot, and on the far right hand, I'm going to add in some new scales here to measure over basin precipitation. That is precipitation averaged over the entire basin, including both the lake surface and the land surface. So what we're looking at here are the long-term measurements of precipitation over each of the Great Lakes. The green vertical bars that you see here represent annual total precipitation over the basin that is above the long-term average. Correspondingly, the orange bars represent annual total precipitation values below the long-term average. And when we look at this data, we see some pretty interesting trends. On Lake Superior, we see that precipitation patterns seem to be oscillating perhaps on sort of a natural cycle with, over the past several years, perhaps below average precipitation. But when we look at the other lakes, we see an interesting trend. Particularly on Lake Ontario, we see what appears to be an increasing trend in the magnitude of precipitation. And this is consistent with a lot of other data that's been collected and a lot of other climate models as well, suggesting an increase in the total magnitude of precipitation. What's not expressed here is an expected increase in the variability in individual precipitation events as well. What's interesting is if we plot on top of this the long-term trends in annual average water levels, we see some interesting patterns as well. For example, on Lake Superior, we see that it appears that water levels on an annual scale tend to respond quite well to changes in precipitation. But then we look at the middle lakes here, Lake Michigan, Huron, and Lake Erie, we don't see quite as clear a response, particularly when we look at the changes in the past 10 to 15 years or so. The relatively steady annual precipitation has been occurring, yet we experienced a significant drop here in water levels. We can look at other variables as well, and there's, in fact, a broad range of variables we could explore. I don't have time to explore them all today, but I did want to look at evaporation. And when we look at evaporation, what we see is, of course, a significant trend here, an upward trend in evaporation rates over all of the Great Lakes, most notably on Lake Superior. And when you look at the research that some of our climatologists here at the Great Lakes Environmental Research Lab are doing, most notably Brent Lofgren and Gia Wong, is that what we might be experiencing here is sort of a positive feedback mechanism in which the extent of ice on the Great Lakes, particularly Lake Superior, is diminishing. And that's exposing the surface area of the lakes that's available for evaporation. At the same time, the temperature of the water is increasing, the temperature of the air above the lakes is increasing, all of which might be contributing to increased evaporation rates and subsequently an increased rate of loss of water off the surface of each of the lakes. When we plot water surface elevations on top of this plot, we also see some interesting patterns. We see, of course, that Lake Superior seems to be dropping in water surface elevation over the past 20, 30 years or so, and perhaps in response to increases in evaporation. But when we look at the Middle Lakes, we see a much stronger relationship between this increase in evaporation over the past several years and the drops in water levels. Now, certainly evaporation doesn't explain it all, and in fact, none of the variables that I've shown here, neither precipitation nor evaporation, explain all of what we're seeing here. The fact of the matter is that these are interacting in complicated ways, and we want to try to find a way to express those interactions to make better forecasts in the future of water levels. So what are some of the take-home messages from the observations I've just shared with you here? Well, we can look at water levels at a variety of different spatial and temporal scales. And all of those different temporal scales in particular have different impacts that we need to consider. On an hourly and daily basis, some of those fluctuations are what really could cause significant damage. But in terms of long-term modeling, we often look at things in terms of annual and sometimes even monthly average water levels. There are obviously multiple sources of uncertainty and variability. In our water level gauging stations, in the data that we collect regarding the climate, one of the ones I underscored here today is the idea of isostatic rebound and how it affects the water level measurements we take. No single factor, whether it's natural or non-natural, is going to explain it all. And what this points to is a key research question, which is, can we relate these variables, can we reproduce them, and can we use them together to predict water levels using models? And that leads into the next section of my talk here. Now, there are a variety of different models that can and are used here in the Great Lakes system. I'm just going to use one of them as an example today, and that model I'm going to use is a model that was developed here at the Great Lakes Environmental Research Laboratory by Tom Crowley, which is the Great Lakes Advanced Hydrologic Prediction System. Now, what we're seeing here are a set of nodes and arrows that represent a flow of information through the model leading from raw meteorological information data here all the way down to water levels. And there are a variety of different models that can combine this data in different ways, use different algorithms, but the building blocks are often the same. And those building blocks include, first, model algorithms that combine the data and attempt to develop lake-wide and basin-wide averages of those data in areas where we don't have information, and in fact, for some variables such as evaporation, where we have really limited or no information. The next step would be then to combine those into the major components of the hydrologic cycle, which we refer to as the net basin supply. And regardless of the model algorithms we use in the upper part of this model, typically we ultimately try to calculate the net basin supply. That is the combination of runoff, precipitation, and evaporation. And even if we have those natural factors, we still need to somehow express how the interconnecting channels, how water flows through the interconnecting channels and the impact that has on water levels. And that's just not a reflection of how the waters, the levels on Lake Superior and Ontario are regulated, but there are other factors as well, such as when the channels might be dredged, when algae forms on the channels, or even when there are ice formations on the channels that impede flow. And then finally, all of this gets put together into a forecast of water levels. Now, one of the important steps in using any model, whether it's this AHIP system or other models, is to continuously assess the skill or the performance of the model over time. And we recently did this with the AHIP system in a paper that is currently in revision with the Journal of Great Lakes Research. So what I'm showing here are a set of empty plots. I'm showing here Lake Superior, Lake Michigan-Huron, and Lake St. Clair, and Lake Erie. For this particular study, we did not include Lake Ontario due to some of the complications of the regulation plan. So I'm going to put up first here what I'm referring to as the 6-month out forecasts that were generated from 1998 through 2010 using the AHIPS model. These vertical bars represent a 90% prediction interval made for a given month 6 months prior to that month. And these prediction intervals essentially represent the uncertainty and the variability in future meteorological conditions. I can also put on top of this plot the 3-month out forecasts, and then finally on top of that I can put the water level or the average monthly water level that was ultimately observed. And what we see here in general, without going into too much detail, is that this particular model does a reasonable job of reproducing water levels on a seasonal basis anywhere out up to 6 months ahead of time. So what are some of the take-home messages from the modeling portion of my talk here? It is absolutely imperative that any models that are used for long-term water level forecasting here in the Great Lakes, and they're used to reflect climate change scenarios, are continuously assessed for their skill, and that they're continuously improved to reflect changes in data. It's also important that within the Great Lakes here, we continue to pursue funding to maintain and expand the monitoring infrastructure network we have, and that includes, just as an example, the rain gauges, the flow gauges, and even some of the evaporation measurement stations we have here in the Great Lakes. Maintaining and expanding those is absolutely critical. And one of the nice things about models is that we can often use models to capture where we have the greatest uncertainty in our understanding of the hydrologic cycle. And we can use those results to focus our efforts to fill in gaps in the monitoring network that will provide the greatest reduction in forecasting uncertainty. And then finally, it might be already apparent, but when we have multiple different models, multiple model algorithms, and a variety of different inputs, in this particular case, different ways of calculating evaporation, different ways of estimating over-lake precipitation, and different ways of calculating runoff, coupled with the uncertainties in those measurements, we can have a range of different results. And that's what this last part of my talk, I think, is going to emphasize. So let's take a look here at what we've come up with in terms of water level forecasts. I'm going to start off here with a quick example of some of the climate forecasts that have been made. In general, the way these water level forecasts are made is a model similar to the AHIPS model, or in fact using the AHIPS model that I talked about earlier, is coupled with variables from a larger scale regional climate model. And that the output from a regional climate model is downscaled so that it's compatible with the water level models that we're using here on a Great Lakes scale. Let's take a look at just one of the variables from one of these regional climate models. Again, I want to emphasize there are multiple different papers out there demonstrating a variety of different regional climate models. I'm just going to show one of them here as an example. So let's take a look here. Here is the precipitation data that I showed earlier, and I want to put on top of this results from a paper by Philip Chow that was published in the Journal of the American Water Resources Association in 1999. Dr. Chow presented a variety of different models, 4 of which I'm going to highlight here in this talk. The first of which is a set of precipitation forecasts using the Geophysical Fluid Dynamics Laboratory transient model, and the results of that one are shown in these series of black dots here, both for forecasts made out to 2020 and then again out to 2050. And for all of the Great Lakes systems, that particular model seems to indicate we might expect a rise in the average annual precipitation values. We can plot on top of here the model results from the other 3 climate models as well. And ultimately what we end up seeing here is more or less a broad range of potential changes in precipitation across all the different models. And this, what this underscores is the fact that there truly is a lot of variability in the future climate model scenarios. Again, these are the results for just one variable in the entire hydrologic cycle. We could plot similar results for evaporation and for runoff that might have comparable scales of variability. And again, this is just from one particular paper using one set of models. When we shift over into looking at how these changes propagate into water level forecasts, I want to start off here with an image from a paper that was published last year in the Journal of Great Lakes Research by Catherine Hayhoe and her colleagues, including Tom Crowley, that utilized the Advanced Hydrologic Prediction System to make long-term water level forecasts. And so what we're seeing here is a forecast of water levels on the four major lake systems that indicates a change in the mean lake level in meters over certain time periods. And what this figure suggests is that we might expect, by the end of the century, a drop in water levels on Lake Superior on the order of maybe 0.2 of a meter or so, and then a drop on Lake Michigan and Lake Michigan-Huron of maybe 0.5 meter or so. Now, what this paper does in fact articulate, but is not clearly represented in this image, is that these dots are based on a sort of worst-case high-emissions greenhouse gas scenario that, again, represents almost a worst case. When you read the paper in detail, what you find is that under a low greenhouse gas emission scenario, there was really very little noticeable change in lake levels at all. And that's one thing that isn't readily apparent in this figure, yet this figure is often used in other reports as an evidence of climate change impacts on water levels and drops over time. Another important feature I want to point out in this image that I hope we all remember moving forward is that these are change in lake levels relative to a particular time period. In this particular case, these are changes relative to the average water level between 1961 and 1990. Now, if we transpose these results onto the images that I showed you earlier, we get an interesting image. What I'm going to do is, if you look here at this legend, I'm going to show both the low emissions and the high emissions scenarios, or the forecast based on those two scenarios. The sort of low greenhouse gas emission scenario I'm going to put up as a green line, and the sort of extreme high greenhouse gas emission scenario I'm going to put up as a red dashed line. And let's start with Lake Superior. So what we see here are the annual average water levels over these three forecast time periods relative to the 1961 through 1990 annual average water levels. And at least on Lake Superior, what we see is that for these two extremes, we may not expect much of a change in the long-term average. Now, certainly there might be increased variability about that average, but according to this particular model, not too much of a change. When we look at the lower lakes, though, we see kind of a different story. If we look just at the next sort of 20, 30 years or so, we see that on Lake Erie and Lake Ontario, we might not be expecting much of a change in the annual average water level. And in fact, on Lake Michigan and Huron, we might actually see a repeat of some of the long-term cycling we've seen in the past. But yet when we look even further out to 2050, 2080, and beyond, this particular set of model assumptions and scenarios suggest that under a low greenhouse gas emissions, while we might not suggest much of a long-term change, under a high greenhouse gas emission scenario, we might indeed expect a rather significant change in the long-term average water levels. To put this into perhaps clearer focus, what I want to do is I want to carve out the water level dynamics we experienced between 1961 and 1990 and overlay them on top of this sort of new average to get an image of what this might look like under this worst-case scenario. So let's do that first with Lake Superior. And what we see here is that the water levels in the future under this particular scenario would vary indeed, and in fact we might experience water levels that are more often lower than what have been experienced in the past. When we do the same thing for the middle and lower lakes, we see an interesting pattern as well, where in fact the low water levels likely would be lower than what we've experienced in the past, but that there's quite a bit of variability around that mean as well. In fact, we might expect that variability to increase, although that's not particularly evident in this particular model forecast. Now, there are other studies that are being done as well, and I want to emphasize that point. One of the other studies that has been done recently by Angel and Kunkel, also in the Journal of Great Lakes Research, published in 2010, looked at a broader range of model scenarios, but also using the Great Lakes AHIP system. And what we're seeing here is an image of forecasts for the Lake Michigan Huron system. Each panel represents an increasing intensity of greenhouse gas emissions. So panel A represents a relatively low greenhouse gas emission scenario, all the way to panel C, which represents sort of a high greenhouse gas emission scenario. And what we're seeing here, of course, is that as we march through time from 2020 to 2050 out to 2080, we see a very significant increase in the variability of our forecasts to the point where on the Lake Michigan Huron system, under this high greenhouse gas emission scenario, we might expect water levels to rise relative to some existing benchmark of anywhere up to a meter or so. We might also expect things to drop by perhaps anywhere on the order of 1.5 to 2, even 2.5 meters or so. Again, one of the points here is that these are all based on some departure from some common reference point. So to wrap things up here, what are some of the ultimate take-home messages and conclusions from this talk? Well, first of all, there is certainly lots of variability and uncertainty in these long-term forecasts. And hopefully I've laid down a foundation for some understanding of where that variability comes from, both in terms of the measurements that we take and also in terms of some of the climate variables that we monitor and that we forecast using regional climate models. Second, I want us all to recognize that for any one of these forecasts, it is important to acknowledge what the baseline conditions are against which they're being compared and to put them all into some long-term historical context. And then finally, what this all really points to is a need for adaptive management, which represents a combination of three major steps: the ability to observe what is happening in our environment, and that's maintained by an environmental monitoring network, the ability to refine our management strategies and also our models, and then continue to improve how we adapt to different changes in water levels and climate scenarios, and how we make improvements in our model forecasts. There's a lot more information on all of this. You're certainly welcome to send me an email if you have any questions. Our lab's website is www.glurl.noaa.gov, and the Climate Services webpage, that is NOAA's Climate Services webpage, has a lot of information about regional and global climate change, and that's at www.climate.gov. And before I wrap things up, I do want to give out some acknowledgments. First of all, thank you to Jill and Ohio State University for the invitation to speak today. I also want to thank several folks here in the lab. Particularly, I want to thank Tim Hunter and Ann Kleitz, who have spent a lot of time, not just over the last few weeks, but over the past several years, on the order of 15, 20 years, developing and maintaining the data and the models that went into this presentation today, and they deserve a tremendous amount of thanks. I also want to thank Brent Lofgren and Craig Stowe in particular for providing some feedback on this presentation. I also need to thank Frank Quinn and Tom Crowley. Many of you in the Great Lakes research community know them. They've spent careers on the order of 30 to even 40 years studying this system, and they've been very generous with their time in terms of providing input. And then finally, I want to thank, of course, not just NOAA for the support for our laboratory, but also for our federal partners as well. The research that we do here and the work in the Great Lakes represents a collaboration across a broad range of sectors. And the collaborations that we have here between US EPA, USGS, the Army Corps, and indeed even Environment Canada, I think are worthy of noting, and I'm very appreciative of those collaborations. That concludes my talk today. Thank you again for the time and for listening, and I'd be happy to field any questions.
All right, thank you. That was great. Let me get started, and we've gotten some great questions during the presentation, so I'll ask Dr. Grunewald as many as we can, and what questions he can't answer today by one, we'll post later on the website with his answers. We've gotten several questions dealing with measuring water levels, and specifically one question that we had was in terms of is volume a good measure to rank the world's inland water bodies? That was one question. And then also, in terms of the historical aspects of water levels, was water level being measured in a way that allows us to compare data in the 19th century versus today?
Okay, I'll start with the second question. In terms of comparing water level measurements over time, there is, in fact, an algorithm that has been developed for adjusting water levels at various points throughout each of the Great Lakes over time and over space relative to one another, so that we can compare them over time. And I need to acknowledge that the effort that was put into that, there are a lot of folks in the Great Lakes community who developed those equations and apply them. Frank Quinn and Ann Kleitz from Great Lakes Environmental Research Laboratory here were instrumental in applying those equations to the data that I presented to you here today. In terms of looking at the Great Lakes on a basis of either water surface area or volume, there's certainly a wide variety of other metrics that we could use to stack up the water bodies on the planet. Those are just two that I thought would underscore the magnitude of the freshwater resources that are available and to put into context the ones here in the Great Lakes.
Okay, great. Another question we had was if you could comment on the potential uncertainties in the long-term data sets that you had shown, the lake levels, the precipitation, the evaluations, and the measurement technologies that have changed over time.
Okay, so I'm guessing that the question has to do with the fact in terms of measuring water levels, are we getting more and more certain of what the water levels are over time? I'm going to have to get back to you on that question. I would want to talk more with the folks in other branches of NOAA who are more familiar with the exact instrumentation of the water level measurements. Although in general, I'd have to say the measurement of a water level at a particular gauging station, the magnitude of that variability is probably not all that high. Now, what has changed is our understanding and our understanding of the variability of water levels around all the Great Lakes, and in particular, the algorithms and the tools that we use for combining the different gauge information across all the different lakes to develop long-term averages.
Okay. Another question we had was, has the variability that we are currently seeing in long-term forecasts always been there? Or are there specific climate change factors or indicators that are influencing that variability for lake level forecasts?
Okay, Jill, would you mind repeating that question one more time?
Sure. Has the variability that we are currently seeing in long-term forecasts always been there? Or are there specific climate change factors or indicators that are influencing variability in the long-term lake level forecasts?
I'd probably look for additional feedback on that question from some of our climatologists here in the laboratory. But as sort of a partial answer, I'd suspect that as we march through time and continue to improve our regional climate models and our methods for downscaling the information from the regional climate models, the variability in the future climate model conditions might in fact decrease a little bit. One of the interesting sort of segues from that question is that we're sort of entering a very interesting time period here where the forecasts of climate variables and the long-term forecasts of water levels and our observations are starting to overlap. And it sort of represents a really interesting opportunity to start comparing how the uncertainty and variabilities in those forecasts compares with what we're ultimately observing.
Great. Another question that we had, as a person who has reviewed all the models and done many yourself, do you believe we are accurate in telling people that both precipitation and evaporation will increase and the frequency of severe storms will increase, but predicting water levels is the most challenging? What is your final forecast on future water levels on each lake, up or down?
I'm not at the point in my research where I would make a conclusive response to that statement at this point. I think the best research that's been done on that, or one of the best sets of research, are the papers that have been presented, in particular Angel and Kunkel's paper. When we look at that particular paper, it suggests, which I have on the screen right now, over a broad range of forecasts, under a broad range of different conditions, it suggests that the median of all those forecasts, which on the slide I'm showing on the screen right now is the dark horizontal red line, is sort of gradually going down just a little bit. So I guess the overall consensus under this particular set of models is that long-term average water levels may be slightly decreasing over time. But I would have to put that within the context of the fact that we're making forecasts, in this particular case, 50, 60, 70, 80 years into the future, and that we would really need to couple that with sort of ongoing updating and refining of our models as more information becomes available. So I'm not really prepared to make a conclusive statement about what I believe water levels are going to do 80 years from now.
Okay, we had another question about some of those predictions, and specifically one viewer had asked, can Dr. Grunewald comment on the relative influence of various water level drivers, such as climate change, lake level management, connecting channel alterations, and what factors are most likely driving water level trends?
The general consensus, there's been an awful lot written about this and obviously a lot of publicity and commentary. The general consensus among the scientific research community is that the major drivers in long-term water levels are indeed the major components of the hydrologic cycle and the changes in those major components due to future climate scenarios. However, we also do include in some of our long-term forecast models some of the regulation plans and the changes in the interconnecting channels. But again, I think most of the long-term patterns we expect to be a derivation of changes in the major components of the hydrologic cycle and how they respond to climate change patterns.
Okay, well, actually it looks like we're almost out of time, and so what I wanted to do was let everyone know that questions that we haven't been able to get to will be given to Dr. Grunewald, and we will have those answers posted on the website with the archived webinar in about a week. I wanted to, again, thank Dr. Grunewald for his willingness to talk to us today about Great Lakes water levels and the impacts that we could face with a changing climate. A really great discussion. I also wanted to thank the NOAA National Sea Grant College Program and the OSU Department of Agricultural, Environmental, and Development Economics for funding this particular webinar. I did want to remind you that our survey URL for this webinar is in the chat feature. Actually, it will be in a second. Please take a few minutes to fill that out. I also wanted to refer you to resources and our archive of all previous webinar presentations, which are located on our changingclimate.osu.edu website. This webinar series is sponsored by the OSU Climate Change Outreach Team and will continue next month with the presentation by Ohio State University's Dr. Greg Heitsusen, who will be discussing how environmental ethics and religion influences climate change beliefs. That will be our last webinar for the season, but the series will start up again at the beginning of the new academic year in September. Thank you again to Dr. Grunewald and all the participants on this webinar. We hope that this was beneficial and hope you will join us again in the upcoming webinar. Thank you and have a great afternoon. The URL will be on right now. Thank you.